Okay, thanks a lot. It's a pleasure to be there. So I feel a bit like an outlier with almost 60. So I did machine learning where most of you were not even born. So so what I will try to explain today is I think it will be the end of a long winter of Bayesian techniques in machine learning, and I will try to explain you why. I will more or less look only at a single problem, which is most classical problem in machine learning, which is called supervised learning, like trying to recognize between dogs and cats. And I will try to explain why the dominant paradigm, which was not Bayesian, by the way. Bayesian statistics is a very, very important field in many, many domains, but Bayesian techniques are not so important in machine learning today. I will explain why Bayesian techniques there will be a big comeback, I think, in the next future. Okay, we try to at least convince you. I'm convinced that it will be like this. Perhaps it will not be true. Okay, so what is so machine learning techniques have a very long story. So the idea of supervised learning comes to the 60s when I think the first perceptron is 58. So I was was very young. So when all this story started, and so it's a paradigm which is very easy, where you try to predict labels, you try to predict labels from features, and there are many works, especially started from say 70s, 80s, ending up in the 80s with what is called now a shallow neural nets to do this. And in fact, if you look at the theory of this was really formalized at the end of the 80s, beginning of the 90s, and especially there will be a big name in this, at least theoretical. The main contribution comes from Vapnik, Shelvoninsky, the Russian school in machine learning, which was able to really to conceptualize what you should do, and this school end up with trying to look at the problem in a way where when you have training data, what you will typically do, and this is what when you do supervised learning you still do a lot. You choose your favorite loss function, so you will compute some kind of empirical risk. So this is the empirical risk, and then you will, in order to penalize more or less the complexity of the models, and you will add an additional term, which is called a penalty term. And this penalty term is there are many ways to choose the type of penalties depending upon the structure of your model. And the learning problem basically is an optimization problem. So there is nothing Bayesian there. So simply you need to hire a very good guy able to perform optimization, perhaps in super large dimension. And behind this are a lot of results which are, I think, very beautiful in terms of mathematics. I think there are almost all places that are not very useful in practice, but it's very useful. So you can obtain generalization bounds, pack bounds, Vapnik-Shelvoninsky complexity. So there are many ways. There are many nice results. Not perhaps very useful, but at least they are there. And it goes like this for about 20 years. It was really in machine learning, I say, the kind of Bayesian winter. So at least in supervised learning, and so something happened in 2007, 2010, which is the appearance of a completely new paradigm, which is deep nets. So what makes deep net different from the classical machine learning stuff is that first you have a dramatic increase in the number of parameters, and I think this is why Bayesian techniques are useful. There are also a dramatic increase in the size of dataset, which is welcomed in most of the time, but of course it causes a lot of problems when you try to start a compute. There was also a parallel development of the performance of computer architecture, and also now the availability of very powerful tools to speed up the development of this type of techniques. There are, of course, current limits of machine learning. This is why you are there. Otherwise, the problem would have been solved. I think it will be there for at least 50 years. So first, the techniques are very data hungry. So millions of examples are needed. And there was, as mentioned by Joshua, in fact, typically, computers need much more data to learn because they don't learn concepts. They really learn only from data. The computational complexity is massive. Something which is also, I think, a bit problematic is that making this type of algorithm work is really an engineering art, which regards great expertise and trial and error tuning. So you all know that. So it's very difficult to learn this type of stuff. There are a lot of choices that you should implement, and large number of hyperparameters, which in the performance or the techniques would hardly depend upon these parameters. And of course, there is also a lack of rigorous criteria for choosing an AI architecture over one another. And this is one of the main weakness. So this is why it is a kind of an art. And I think the theory is there, because there is a theory of net. For example, Peter Bartlett writes the Vapnich-Charbonnicki's complexity of neural net, but I think it's the results he obtained are not necessarily very useful. And also another problem which has already been mentioned, of course, because it's there, it's a black box, and it's lack of transparency, and of course it's also very difficult to trust. So now I will explain my own very biased interest, and which is about uncertainty quantification. So I did a lot, as already been publicized by Florence. What I did a lot of Bayesian techniques, and Bayesian techniques are very, very useful in statistics in general. And there have been big success of statistical methods. So in machine learning, Bayesian techniques, Bayesian networks have been very popular in the 90s. They are less popular now, but perhaps there will be a comeback. But my interest comes from the part that since machine learning techniques will be incorporated in many systems which affect quality of human life, you need to be able to trust, to be confident in the decisions that they do. Okay, and what I will try to illustrate in the next slide is that most of the machine learning techniques which are known so far are very bad at representing uncertainty. Since they are very bad at representing uncertainty, for example, they typically don't know what they cannot detect what they don't know. And they are overconfident in their decision. And because they fail to detect what they don't know and overconfidence in their decision, they are very sensitive to adversarial attacks, as I will show now. So I will start with an example from Ian Goodfellow. So it's a classical example. So it's not so, as I said, it's not so worrying in some sense. You start to look at this panda, so you detect a panda with the confidence was obtained by it's a very, very simple softmax confidence, so it's not designed to be so the probability that you obtain in softmax is not a probability of it's not really a Bayesian technique, it's really a number, so you should not trust it too much. And if you add something which look like this, so it's a kind of noise. Of course, it's really an adversarial noise. So it's very adversarial in the sense that it's a noise which has been forced to fool the system. So and the size of noise has been chosen in such a way that you cannot detect. So when you add because these images are pixels which have been quantized, so which means that the amount of perturbations that you do of each pixel is within the range of the quantization interval. So it means that you cannot detect, it's really the size of perturbation is the size, it's one pixel, one level pixel at most. But and what happens then is that now you detect. So if you look at the image, it's impossible to see any difference. There are of course some difference, but you cannot detect any difference. And then the machine starts to detect a gibbon with a confidence which is 93. Okay, so it means that you can create, so with a very, very small perturbation, you can create a fake example, and you can fool completely a very good classifier. So of course it's a bit, as I said, it's not an agnostic attack. So it means that it's an attack which is not agnostic in the sense that you really want to fool the model and you go more or less in the direction where you know that something wrong will happen. And when the explanation is easy, it links with the fact that you are trying to do a decision in super large dimension, and when you do decision in super large dimension, when you do super high dimensional statistics, then there are a lot of very, very special things that may happen, which are linked to this dimension. Something which is a bit more worrying. No, this is an example, another example. Another example where this one is very easy to produce. It's you simply train a shallow neural net on a MNIST database, so you obtain an error rate which is 0.01%. So perhaps I think it's very, very easy. So I think it's a kind of, and then what you do is that you just more or less tweak a little bit the examples, and you will see that you completely fool the system. So this one, this is a 3 which has been rotated, and then it detects 1, but it detects 1 with a super large probability. Okay, so which means that here again, it's an adversarial attack. It's a very, very simple adversarial attack in the sense that you have modified a bit, so you shift, of course, the concept. And something which is, it's a very recent paper. It's a very nice paper, which appeared in the last in its last NIPS, I remember well, or ICLR, I don't remember. But it's a paper by people from Bosch, so which are trying to do autonomous car, and what were doing is agnostic adversarial attack, in the sense that it's an adversarial attack on a semantic image segmentation techniques, where with using an adversarial attack, and it's not clear here, but in fact, if you look at the pictures, they are high dimension. In their publications, they have a super high resolution picture where they show the attack. It's almost impossible. So they use a texture on the gradient. So it's a very, very simple attack. So it's not a sophisticated attack like a good field attack. It's simply you add some kind of texture on some part of the image, and you simply, in the semantic segmentation, you simply erase the presence of pedestrian, which is a bit, for an autonomous car, of course, it will be a bit annoying, because you will start to detect, you will start to kill. If every day you have 10 persons which died under autonomous cars, the popularity of AA will be, of course, it will be less popular. There is another important domain in machine learning where it's important to know what is uncertainty is reinforcement learning. So reinforcement learning, you know the classical work. So in reinforcement learning, there is a trade-off between exploration and exploitation. So you exploit what you already know, and you try to take advantage of what you already know to maximize your reward. And at the same time, you need some time to apply some exploration step in order to better understand your model. So you will sometimes play suboptimal action in order But if you want to do this, it means that when you want to more or less tune the trade-off between exploration and exploitation, it means that you should have an uncertainty of on the things that you don't know. So it's very easy to do this when you do very simple reinforcement task, like, for example, bandit or things like this, because it's easy. So what you don't know, perhaps, is because uncertainty. Imagine that it's a multi-arm bandit problem. The uncertainty is simply the variance of one arm, so which is something which is not difficult to quantify. But in more complex model, of course, when you look even at a Markov decision process with a large number of actions, it's much more difficult then to get useful information about the uncertainty. So I think uncertainty quantification is very useful also in reinforcement learning. So what are the sources of uncertainty in machine learning? So there are basically two sources of uncertainty that we have to take into account. So there are, of course, what is called the random errors. So random errors, it's easy to understand. It's about what noise that you put on your sensors. So perhaps you have missing data, or you have wrong labels, or perhaps you are trying to solve a problem where some observation which are very useful have not been recorded, which is called latent data. So latent data more or less need to be reconstructed with some errors from the existing observation. And there are another source of errors which is very, very important in deep learning, and because in deep learning the structure of the model is very, very complex, is an epistemic error. And you have two sources of epistemic error. So you have the error which is linked with the uncertainty in the parameters. So, because it is well known that the weights in DeepNet are very poorly specified. So, because most of you, I think, have played with DeepNet, you know that if you stop your procedure, say, in advance, you will end up with parameters which are completely different than if you stop the parameters earlier or before or later, whereas if you look at on the training set or even a test set, it will not modify much the result. So it means that there is a lot of uncertainty in the parameters, especially because you know that good minima are flat minima. So good minima means that you are in a region where if you move a little bit, it will not change much the results. And there is also an uncertainty which is linked with the architecture of the parameters themselves, so which means that there are many architectures which can be chosen, so which means that there is a problem of model selection which can also be solved using Bayesian techniques. Why being Bayesian? So you need to be, you can be Bayesian because the Bayesian method is really the way to try to address this type of issue. Because with Bayesian methods, you are able to rate the quality of your prediction, and why you need to still to be Bayesian, because it's also a way to deal in a very principled way with uncertainty in the estimate, because you more or less marginalize with respect to parameters and models. So this is my holy grail. It's typically what you are willing to do when you do, if you are able to perform a full Bayesian analysis, so which means that this would be for a regression problem where instead of predicting points, you are willing to predict perhaps complex distribution. So in some models, it's worked very well. So for example, when you do target tracking or you are able to do things like that, and of course when you do classifications, you would of course be happy to get a result like that, which and of course these results have been obtained in very small dimensions, so it's more or less toy problems, and my goal is to try to do that for real applications. If you do a MNIST, if you simply take the same example and then when you perform a Bayesian techniques, and it's a very simple stuff. So what you do typically there is you apply simply a Bayesian method, not on all the weights of your neural net, but only on the last. So you consider that in neural net all the deep layer or conv layer are extracting features, so you don't. This is not where the uncertainty need to be taken into account. So you start to look at uncertainty in the output layer, and you obtain then a rather satisfactory uncertainty estimate. So this is the first result obtained by Nicolas Brosse, who is a PhD student working with me, and which is now working at Google in Zurich. So he's working on this topic, but no longer with me. Thanks for your attention, and I will be happy to answer questions.